Hello everyone. Let's take a few moments and let's work through the converse of the mid-segment theorem. So I have a little picture here. You have a triangle, any old triangle, doesn't have to be anything special about it. And we have a line which is DE. And this D we know is the midpoint of one side. So D is the midpoint of AC. That's one of our givens. And we know that DE is parallel to AB. So we know that this right here is parallel to that right there. So that's what we know. And then I just made this line go on for forever because, well, I know I'm going to want the picture to look that way, but also because it could go on forever. That would be fine. And so what we are going to prove then is we are going to prove that E is the mid-segment, or midpoint rather, of BC. So we're going to prove that E is the midpoint. So if it starts at a midpoint and if it's parallel to the base, then this should be the midpoint of that side. And we are going to prove that. Okay, so let's put this over here and let's do statement and reason. Let me see, how many points did it only took me 9 steps to do this. Isn't that great news? Okay, so let's see. Our first statement is our givens. So we know that D is the midpoint of AC. And we also know that DE is parallel to AB. Those are the two things that we know that are given. All right, great. So now what are we going to do? Well, we're going to mark what we know about these two lines here. We know that this is congruent to that, right? We know that AD is congruent to DC. Why do we know that? Well, because that's what midpoint means, right? Midpoint means that you are cutting it directly in half. So those two are going to be congruent to each other. Okay, and then what we're also going to do is we're going to start labeling some of these. I'm going to label this angle right here as angle 1, and this angle right here is angle 2. And I'm going to be able to say that these two angles are congruent to each other. Now you're thinking to yourself, how did you know that you were going to have to do that? It's because I've done this proof about 8 bazillion times now. But that's the way you do the proof. So there you go. All right. So number 3 says that angle 1 is congruent to angle 2. Why is that true? Well, the vertical angle theorem lets us do that. Right? The vertical angle theorem says that if you have 2 vertical angles, then they are going to be congruent. And ta-da, they are. Okay, so now I'm going to say that there is a point F on line DE such that, can we still read that? There we go. Such that DE equals EF. So there's some point, let me see, this goes, so this goes, so about here, there is some point F. And the reason that I'm able to make it exactly equal to DE is because of the ruler postulate. The ruler postulate says that I'm allowed to measure my segments like that, and it'll make sense. So that's what I did. All right, so now I'm going to move this over here, and I'm going to continue my statement and reason over on this side. All right, and so you can see that we have some triangles. You can imagine a line here for a triangle. You can see that we're going to have some triangles to come together. And so we know from previous experience that we're probably going to want to make those congruent to each other. But if you look carefully, at what we have proven so far for this triangle, we're going to have an ASS, which is not going to help us, right? ASSs do not help us. They hurt us. Well, they don't hurt us. They just annoy us because they don't help us prove congruence. Now, maybe we could get away with it if these were right triangles and we could use some hypotenuse leg theorem, but we didn't draw it like a right triangle, so we can't do that. And so I'm thinking to myself, well, how am I going to get these other angles equal to each other? And finally, I decided that the best thing for me to do, which I will do in step 5, is to draw a line through F that is parallel to AC. So I'm going to draw a line that's parallel. And just because I don't want to assume that it goes through point B. So it would be very easy for me to just do that. And actually, in real life, it does go through point B. But I don't want to assume that. So I'm going to intentionally draw it so that it doesn't go through point B. I know that makes my lines not look parallel, but really, who cares about that? Because I'm going to put those little arrows on them, and then everybody looking will know, oh, she just draws poorly. But I want to make sure that I don't accidentally catch myself relying on this line going through B. Okay, so that's how I'm going to draw it. Okay, so why am I allowed to draw this line that is parallel to AC through F? Well, that's the parallel postulate, my friends. Remember, that one says that for any point P not on L, there is exactly one line through P that is parallel to L. That's what we got going on here. So that's what I did. Now, I wanted these two lines to be parallel because I want to be able to make these two angles congruent. And I can do that if they are parallel lines, because I can use my AIP formula here. So I'm going to say that angle 3 is congruent to angle 4 because of the AIP theorem. Did I just call it a formula? I think I did. It's not really a formula. It's a theorem. Okay. So now I have angle 3 is congruent to angle 4, and now I'm happier because now look at, now I have an ASA, So I can say that those two triangles are congruent to each other even without having my drawing done perfectly. So triangle CED is congruent to triangle BEF. And I can say that because of the ASA. I don't even need this to be perfect. So that's awesome. So now that I've done that, I've made these triangles congruent to each other, I can now say that CE is congruent to EB. Right? Because, let me see, CE is congruent to EB. And I can say that because of the definition of congruent triangles. Right? These two triangles are congruent, these two sides match up, these two sides will match up, and these two sides will match up. So that's why I can say that those are congruent, which means that I can say E is the midpoint of CB. And I can say that because of the definition of the midpoint. Midpoint means wax it right in half, and that's what we've done. We have 3 hashes on this side and 3 hashes on this side. And so we have now proven the converse of the midsegment theorem. Now, again, just to make sure you understand what this means, let's just review. It means that if we have any old triangle, I'm going to draw this one like this. And then I'm going to flip it like that. Okay, so if we have any old triangle, if I start at the midpoint of one side and I draw a line that's parallel to the base, then that means that this is also going to be a midpoint. Okay? If I start at the midpoint of this side, I make my line parallel to the base, then that is also going to be a midpoint. That is what the converse of the mid-segment theorem says. Alrighty. Alright, that was good. Alright, now back to our normal programming.